Alright, welcome back everybody. In this video we're going to talk about information from section 6.5 of AP Calculus, interpreting the behavior of accumulation functions involving area. In the last lesson we talked about accumulation functions, and we're going to tie that to information that we've already learned previously. So let's kind of take a look at the introduction. It says here we're going to utilize things that we learned related to the Fundamental Theorem of Calculus, part 1, in our last lesson, and we're going to connect those to things that we learned about the relationship between a function and its derivative from Unit 5. Alright, so let's see. Remember, we learned about accumulation functions like capital F of x, where capital F of x determine the amount of area accumulated under a curve by the definite integral. This function, capital F right here, the integral from a to x of f of t dt. Also remember, by the Fundamental Theorem of Calculus, that the derivative of capital F of x is equal to lowercase f of x, when f of x was defined as being equal to the definite integral. Okay, so keeping all this in mind, let's talk about characteristics related to these functions, capital F of x and lowercase f of x. So suppose capital F of x is increasing. Now what we know from chapter 5 is we know that when a function is increasing, the derivative of that function is increasing. And therefore, when we know that capital F of x is increasing, we know that the derivative of that function is positive. I did say increasing a second ago, didn't I? I meant to say is positive. So we know that when capital F of x is increasing, capital F prime of x is greater than 0. Now, since capital F prime and lowercase f are equal to one another, that means that when capital F of x is increasing, lowercase f is positive. Okay, continuing on. When capital F of x is decreasing, that means capital F prime of x is negative, which means that lowercase f of x is negative. Okay, when capital F of x has a relative maxima, that means capital F prime of x changes sign from positive on the left to negative on the right. And similarly, if capital F of x has a relative maxima, lowercase f changes sign from positive to negative. That's indicative of a maxima. When f of x, capital F of x has a relative minima, that means capital F prime of x changes sign from negative to positive. Which means that when capital F has a relative minima, lowercase f changes sign from negative to positive. So what we're going to be doing with this information a lot is we're going to be looking, from negative to positive. Sorry, that's what happens when I start talking before I finish writing. We're going to be looking at maybe a graph of lowercase f and trying to talk about what's happening with capital F. That's a common thing that we're going to possibly do in this section, which is why it's important for us to understand these relationships. All right, up next, f of x is concave up. That means that f double prime of x is positive, which means that lowercase f prime of x is positive, since the second derivative of capital F is the first derivative of lowercase f. Okay? And when it's concave down, that means f double prime of x is negative, which means f prime, lowercase f prime of x is negative. And if capital F has a point of inflection, that means that f double prime of x changes sign. And it can change sign in either direction to have a point of inflection. So changes sign from positive to negative or negative to positive. And so if we're looking at f prime of x, we're looking for where it changes sign from positive to negative or negative to positive. And so we have a whole lot of information at our disposal based off of these relationships that might exist. So let's go ahead and use that information. Let's start with the first example here. For the graph of f shown below, let g of x be equal to the integral from 0 to x of f of t dt. Okay, find the x values for each of the following and justify your answers. This is a graph of f, not the graph of g. Remember, by the fundamental theorem of calculus, the derivative of the left side here is equal to the derivative of the right side here. The derivative of g of x is g prime of x, and the derivative of the integral from 0 to x of f of t dt is just f of x. So that means that the graph that we're looking at here is actually a graph of g prime. Okay? So in order for there to be a relative maximum of g, we want g prime to change sign from positive to negative. So looking at this graph, g prime here is positive, since it's above the axis, still positive, still positive. Right here it's 0, and then it's negative. And now g prime is negative. It's negative, 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 0, positive again. All right, so we're looking for where g prime changes sign from positive to negative. That happens at x equals 3. And my justification for my answer is that f of x, which equals g prime of x, changes sign from positive to negative at that value. Okay, next, a relative minimum. Oh gosh. Here we're looking for where f of x, or g prime, changes sign from negative to positive, which happens right here. All right. Let's see, where is that? That's 4 plus the square root of 2. Okay. Which you can figure out with a little manipulation of the parabolic portion of this curve. 4 plus the square root of 2. Because this parabola, goes over here, and if I translate this, this is basically just y equals x squared, just translated. So if I go up 2 units, it's basically over the square root of 2 units from its center, and that's why that's 4 plus the square root of 2. And my reason here is because f of x equals g prime of x changes sign from negative to positive. Okay, let's keep rolling. Part C, we're looking for when g is increasing. In order for g to be increasing, that means g prime needs to be positive. And since this is a graph of f, which is the same as g prime, we're looking for where this graph is positive. It's positive from negative infinity to 3. You see this entire graph over here is above the horizontal axis. And then from over here, and that was 4 plus square root of 2, up, okay, there's where it's increasing, because f of x, which is equal to g prime of x, is greater than 0 on these intervals. Okay, decreasing. Well, in order for g to be decreasing, that means g prime needs to be negative. And it's negative here from 3 to 4 plus the square root of 2. And so that's where f of x equals g prime of x is less than 0 on these intervals. All right, g is concave up. That means g double prime is greater than 0. So since we're looking at a graph of g prime, that means g double prime is represented by the slope of this graph. So we're looking for where the slope of this graph is positive. Here the slope of this graph is 0. Here it's negative. Starting right here, the slope is positive, 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 and then 0 again. And so from 4 to 6, the slope of this graph is positive. Okay, and how am I going to explain this? Well, one way I can explain this is by saying f of x equals g prime of x is increasing on this interval. Or that, the slope, another way I could say it is the slope of f of x equals g prime of x is positive on this interval, which implies that g double prime is positive. Okay, g is concave down. Well, so we're looking for where the slope of this graph is negative, and that happens from 2 to 4. So that's going to be our interval, 2 to 4. And there, f of x equals g prime of x is decreasing on this interval. Or I could also say the slope of f of x, which is equal to g prime of x, is negative on this interval, which implies that g double prime of x is negative. All right, and a point of inflection. In order for there to be a point of inflection, I need the concavity to change, the slope to change here on the graph from positive to negative. So the only place where there's a point of inflection is at x equals 4. X equals 4. And one way that I can say this is the slope of f of x, which equals g prime of x, changes sign from negative to positive at this point. Positive at this point. So g double prime of x changes sign at this value. All right, that takes us to the end of our first example. We're going to go ahead and end the video here. We'll come back in a second video and do a few more problems, a few more questions like this one, examples like this one, related to interpreting the behavior of our functions. All right, see you then. Have a great rest of your day, and we'll see you next time. Bye-bye.